standing on a fault line, watching the land itself move beneath your feet, or looking at fossils on different continents and wondering how did creatures cross those oceans? Did they fly? Did they swim? Can you picture volcanoes forming in a line across the sea, or continents that used to fit perfectly together now a world apart? What's the real reason earthquakes, mountains rise, oceans grow or shrink? Welcome to Physical Geology 001A at West Valley College. I'm Professor Farida Box Musa, and today we're demystifying plate tectonics, the most profound, elegant and world-shaking idea in all of geology. Let's zoom back to the early 20th century. Geology was mostly about describing rocks and landscapes. Mountains were a puzzle, earthquakes a curiosity. The idea that continents could move was frankly almost laughable. Enter Alfred Wegener, a German meteorologist with an eye for the big picture. He noticed South America and Africa fit together like puzzle pieces almost too well. But that was just the start. Fossil evidence, identical land reptiles like Mesosaurus and the seed fern Glossopteris found on continents now separated by vast oceans. Rock layers and mountain chains, matching strata and ranges found on both sides of the Atlantic, like the Appalachians and Scottish Highlands, or geological matches between Brazil and Angola. Evidence of ancient glaciers, the Karo glaciation, scratched across rocks on continents now sitting at the equator. Wegener connected the dots and called this supercontinent Pangaea. He argued that it later broke apart, sending the continents drifting. He published boldly, first in Germany, then worldwide. Here's the problem. Wegener had no good explanation for how continents could plow through hard oceanic crust. His ideas about pole flush, forces from Earth's spin, and tidal pull just didn't cut it. With no mechanism, the scientific establishment, especially in Britain and the US, shut the door on his radical model. By his early death in 1930, Wegener was mostly dismissed, and yet his evidence was too compelling to go away. Back then, geologists clung to two fading ideas: contraction theory, the planet's cooling and shrinking, mountains form like wrinkles on a shriveling apple. Permanentism, continents and oceans have always been where they are now, explaining fossil and rock matches with imaginary land bridges across what's now deep ocean. But the numbers didn't work. Isostasy, our crust really floats, and basic earth science could not support these dying theories. Paleomagnetism cracked the puzzle open. As magma cools, iron minerals record the direction and strength of Earth's magnetic field. In the 1950s, scientists found that rock layers of different ages showed apparent polar wandering, as if the pole itself had zoomed all over the planet. But there's only one North Pole. The conclusion: the continents themselves must have moved around, carrying those rocks and their locked-in compass needles with them. Oceanography leapt ahead. In just a few decades, ships mapped the oceans with sonar, showing vast mountain ridges zigzagging down the seafloor, deep trenches near continents and volcanic islands rising from nowhere. The ocean crust turned out thin, young and basaltic, very different from the continental crust. Seismic networks revealed that quakes cluster along mid-ocean ridges and trenches right where plates are born or destroyed. Heat flow is highest at ridges, hot material rising, and lowest at trenches, cool stuff sinking. Then came the zebra stripes. Clever young geologists like Fred Wine, Drummond Matthews, and Lawrence Morley noticed that magnetic stripes on the ocean floor lined up perfectly symmetrically on either side of the ridges. So this is your ridge and these are your magnetic stripes. These bars of normal and reverse magnetism were a barcode of Earth's history, produced as molten lava cooled and locked in the then current magnetic direction, only to be dragged away as fresh lava replaced it. This perfectly recorded the birth and movement of new seafloor out from the ridges. Seafloor spreaded, bringing continental drift out of the realm of imagination and into the world of data. Now let's talk about hotspots. The classic example, Hawaii, a string of islands right in the middle of the Pacific. How are these islands formed? Not on a plate boundary, but from a stationary mantle plume that punches through the moving Pacific plate. As the plate moves northwest, a trail of volcanoes is left behind. Volcanoes further from Hawaii are older and more eroded. So that's the plume. You have your Hawaii mountain, and then again the plate moves, this island moves. And then you have another mountain, another Hawaii island forming. Again the plate moves, and then the mantle plume moves again, another, and then we have our last one so far, the big island where the mountain plume is currently. The superior seamounts extending north from Hawaii all line up. Scientists like J.A. Tarduno and his team used the ages and distribution of these volcanoes to measure plate motion, showing not just plate movement but changes in hot spot position as well. For example, Necker Island is about 10 million years old and sits over 1,000 kilometers from Hawaii, moving at 10 centimeters a year. Suiko Seamount, nearly 65 million years old, is nearly 5,000 kilometers away. Mantle plumes aren't just under oceans. Check out the Yellowstone hotspot in the US or the long-lived Anaheim volcanic belt in British Columbia. And as we explored the seafloor, we found more than ridges and hotspots. Transform faults discovered and mathematically modeled by J2's or Wilson are where plates slide past each other like the famous San Andreas fault. A closer look at the mid-Atlantic ridge shows these offsets aren't random. Transform faults lie between ridge segments, their movement explained by the motion of rigid plates. Wilson went further, formally introducing the idea that Earth's crust is broken into rigid plates, the birth of the term plate tectonics. By the late 1960s, the map was clear. Earth's rigid lithosphere is broken into about 20 major plates, moving from less than 1 centimeter a year to over 10 centimeter a year. Boundaries come in 3 types. Divergent, where plates move apart, new crust forms at spreading centers. Convergent, plates crash together, mountains, earthquakes and volcanoes erupt. And transform, where plates grind past one another sideways. Plates include not only crust but rigid upper mantle. They never leave gaps. As one plate moves, another fills in behind it. Their motion is driven by the soft, partly melted as thermosphere below, allowing them to slide or be pushed and pulled. Divergent boundaries start with doming and rifting. Think like East African rift. Become linear seas, Red Sea, then grow into oceans, the Atlantic Ocean. Ridges are full of volcanic activity. Buoyant mantle upwells, melts and crystallizes as new crust. Oceanic crust formed is always mafic, made of basalt. Convergent plate boundary. There are 3 types, okay? Ocean-ocean, ocean-continent and continental-continental convergent plate boundaries. Let's explain one at a time. So ocean-ocean, one ocean plate subducts beneath another, forms deep trenches like the Aleutians, volcanic arcs of islands. Now continental and ocean. Remember, ocean is more denser material, so it will slide down, continental plate will go up. The denser ocean plate subducts under the continent, like think of Nazca plate and Andes, or the Juan de Fuca plate and the Cascades. And then you have a continent, where I come from, India. When 2 light buoyant continents collide, they crumple upward. Think Himalayas, formed by India colliding with Eurasia. Transform boundaries, and we have an excellent example here in California. Most are found connecting segments of mid-ocean ridges. On land, iconic examples include California's San Andreas Fault and Canada's Queen Charlotte Fault. Here, earthquakes are common, but you don't form or destroy crust. Pangaea wasn't the first supercontinent, nor will it be the last. Before Pangaea, there was Rodinia and Pannotia, all forming and breaking up over hundreds of millions of years as plates drift together and apart, the supercontinent cycle, theorized by Tuzo Wilson. The Atlantic Ocean is opening now because of the mid-Atlantic rifting. Eventually, sediments will overload the Atlantic floor, subduction could begin and the Atlantic will close, driving continents again together. The final big question, what drives the plates? Early models assumed mantle convection did all the work, dragging crust along. Today, most geologists prefer the ridge push slab pull model. Ridge push. At spreading centers, new hot buoyant crust creates a push as it slides off the ridge. Slab pull. Old, cold, heavy oceanic plates sink back into the mantle at trenches, pulling the plate behind them. Mantle convection is still crucial. Without it, we'd have no ridges to push from. Plates with long subducting slabs like the Pacific, Australian and Nazca plates move fastest. Those with less subduction like North America move slower. Okay, so let's summarize it all. Alfred Wegener's bold idea united continents and evidence, but had no engine. Old models couldn't explain how continents or mountains formed, or why fossils matched across the globe. Mid-century discoveries like paleomagnetism, deep ocean ridges, earthquake mapping, heat flow, and seafloor magnetic anomalies cracked the code. The plate tectonic model, Earth's crust and upper mantle are broken into plates that move because of a mix of convection, slab pull, and ridge push. Plates meet at divergent, convergent, and transform boundaries, forming new crust, destroying old or sliding past. The cycle of supercontinents has shaped the entire history of our world. Modern geology is about motion, cycles, and change on a grand planetary scale. Next time you see an earthquake on the news, watch a volcano in action, or even look at an ocean, remember, you're witnessing the constant, magnificent dance of tectonic plates beneath your feet. Thanks for joining me for this lecture, and make sure you do your assignments. Again, come for the office hours. If questions, message me. You all are doing great so far in this course. Keep going, and see you next time. Keep thinking like a geologist.